we did yesterday for this very first problem with this table, trying to find the graph of him. Now, once again, 3 different equations, 3 different tables, 3 different graphs. But in doing number 9, guys, when you go to plug in -1, how do you keep going once you plug it in? It's not as easy as the quadratic is. Flip it. Why? Flip what? The fraction, because what's going on in its exponent?
Negative.
Got it. Exponent rules say whenever there's a negative exponent, we flip. So, wait a minute. Why are we doing the exponent first anyway? Why not just times 4 and let cross out stuff? Is there an order to how we do operations? And what's it called? PEMDAS. And PEMDAS says multiplication first or exponents first. So we have to do this -1 flipping. Wait, what's 4 over 1?
4.
Oh. Oh. So what gets plugged in? -16. All we have to do is flip and then just multiply. Got it. And remember, kiddos, and maybe you don't until you actually start doing it, but we love when we plug zeros into exponents. Because anything to the 0 power is? Oh, no, wrong one, wrong one. Anything to the 0 power is? 1. Anything to the 0 power is 1. I just showed the plugging in because of all of our work with quadratics. I think we've reviewed. You have an x that needs to get plugged in for. We plugged in a -1, then a 0, then a 1. We just talked about PEMDAS saying exponents first, then multiply. Did anybody figure out what happens when you plug in 0? -4? Because Isaiah reminded us, how do you do 1/4 to the 0 again? You get 1. Good. 1/4 to the 0 is 1, but you still have the times -4. So -4 is what gets thrown in the table next. And over here, well, this one's kind of easy too. What's 1/4 to the 1? But just a few of you don't like multiplying. Multiplying, it's right next to, so it's multiplying. It's okay, just a cover next door. You don't like multiplying fractions with non-fractions. Just make them a fraction. Helped one of your classmates yesterday. You can make that -4 and -4 over 1. And how do we do fractions? We go straight across. -4 over 4 is going to be -1. So if you guys notice, it's kind of awkward because I kind of ran into my graph right down here. But when I ran into my graph, I actually don't need any of these y values because if you guys notice, what's true? Oh, I erased that one, sorry. What's true about all the y's? They're all negative, so I don't actually need to. Now, some of you make really good graphs, and I appreciate that. You put tons of tick marks, and it's really good. But to be honest, to save ourselves a little bit of time, you don't always have to do tons of tick marks. For instance, in this one, I'm going to go by 4. It's -4, -8, -12, -16. But on the x's, I'm just going to go by 1s because I just need my, somehow my negative disappeared, I apologize. I just need a -1 and a 0 and a 1. And my 4 somehow looks like an 11. I apologize. But I don't even need any positive values because all of them are negative. So I could graph this negative 16. There he is. I could graph this negative 4. There he is. And then I would have to estimate on the negative 1. But it would be way up higher than negative 4. You guys remember what exponential functions do? Different than a parabola. A parabola is like a full curvature. A parabola is a concave up cup or a concave down frown. But exponential graphs, the ones from chapter 6, they were kind of like lopsided frowns or lopsided smiles. Similar to like a downwards parabola, but it never actually goes down. It's going to keep on swooping, getting closer and closer and closer to that axis. Did anybody notice there was one extra part to this problem? Not just graph, but also domain and range. Is that something we're doing with quadratics, domains and ranges? I probably don't remember. It was before Thanksgiving. I'm sorry. It was the page 243. Quadratics totally had domains and ranges too. So maybe this is something that is going to help us in chapter 8 and in chapter 6 as we review. So let's review real quick. What is domain? Good. And what is range? Okay. Andrew said all real numbers and right away for domain. I was like, yes, solid, good. But some of us need a quick reminder of what domain is. We have in Algebra 1 our green exponent rule book, right guys? Something that I've had you guys referring back to for different things, including like today I said, hey, what's anything to the 0 power? Some of us forgot that, but it's 1. And we've been talking a bit about negative exponents, right? Negative exponents cross the line, change the exponent sign, so a negative with the x squared moves the x squared down. The negative with the z to the 4th move the z to the 4th up. Okay, our exponent rule book, it's good, it's helpful. Some of you need to use that to study. However, in some of the higher classes, we've had something that we used. Now, that doesn't look like an exponential graph. That doesn't look like an exponential graph. Oh, weird. That's like a sideways parabola. And the y is squared, not the x. Huh, interesting. Okay. Ooh. Is this one exponential? Except, the one that we're looking at in our notes right now, is that oriented the same direction? No. Okay, so let's flip them over. We've had some sort of flip happen. I know, ignore that part. Okay, ready? Domain. Oh, it's upside down. Bummer. Huh, that doesn't help. Just kidding. Okay, domain. What do you guys see? Yeah. Domain is talking about x's, and it's asking the question of how far left and how far right. So when Andrew Swanson immediately said all real numbers, was he right? Is this going to keep on going to the left, 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 if I was to keep following that arrow? Yes. And how far is it going to go to the right? To the right, to the right, to the right, to the right. Follow that arrow. Forever. So how far left, how far right? Forever to forever. And what do we answer if it's forever to forever? Technically, it'd be negative infinity to infinity. All real numbers. So ready? This is a great place to use to study for your final. Do you guys have that colored pen out? Here we go. Domain is looking at the x values. And you can do this with parabolas too. And the nice thing is parabolas, I think the reason why you came up so quick with that, parabolas are forever left, forever right, all real numbers also. Looking at the x values, and we ask ourselves, how far left to how far right. So, for this one, what's our domain? What's that snazzy symbol? You guys remember for all those? We could write all we want.
Paragraph.
Paragraph symbol with an R instead. Yeah, very similar though. Paragraph symbol but with an R instead. Now, if domain is looking at x's, come on, you're problem solvers, at least kind of, what would range be? Good enough. Looking at the y values. right is something you do along the x-axis for x values. Okay, help me out. Y values. The questions have to change. Instead of how far left to how far right, x-axis, what do you guys think we're going to do instead? Good. How far low or how low to how high? How down to how up? So here we go. Well, let's see if I have that over here too, because if you guys notice, I had a few little flappies on my graph. I do have my domain, how far left to how far right, all real numbers for this guy. But I also have my range, how low to how high, and now it's the y's. So guys, question, how low does our swoop, look at him, how low does he go if we follow the arrows? How low does he go?
Forever.
Forever. Good. So is there a lower boundary? No. But, question, this is a little bit harder because my flap isn't big enough or long enough. I can move him up a little bit. How high does he? Oh, stink. How high does he go? He doesn't go past what? Okay, let's look at our graph. Sorry, this is a little bit weird and upside down and awkward. Look at our graph. This one's going to be a -1. Guess what? The next one's going to be a square 1/16, a -1/4, and then a -1/16, and then a -1/64, and then a negative. Like, it's so much that you can't even like make any more graph points. It just gets too awkwardly close. Because this guy has what we call a horizontal asymptote, where you can get closer and closer and closer and never hit. Guys, what's this graph never going to go past? 0. Excellent. So, we're asking ourselves the questions. How low? To how high will the graph go? And what do we answer for this one? It has an upper boundary. An upper boundary says, hey, stay below me. Below would be a less than. Stay below who? Stay below 0. We have our domain, and we have our range. Now, we took a lot of time on this first example just because there was a lot of stuff for you guys to review. Maybe if you guys have highlighters, it might be a really good thing for you guys to go ahead and just highlight this domain and range idea. It was important back in chapter 6, and it's important again in chapter 8. Domain and range, how left to how right, and how low to how high. I'm going to zoom back in real fast just in case you want to go ahead and write down the other two problems. Just in case you want to write down the other two problems, we're just not going to take class time to do them right now. But it's something where you can come in and be like, hey, I want to study for my final early. And I can make sure that you have these types of problems down. Does that sound good?
Yes.
Okay. So you have f of x. Remember, you can just be a y if you want. Y equals 3 to the x plus 2. And careful, just a few of you are going to get a little confused. The x plus 2 is all up there in the exponents for that one. So PEMDAS would say, parentheses, you gotta sneak up here and do the exponent first before you can raise the 3 to that exponent. That one has a couple little tricky things. And then some of you also might not realize that this guy, very similar, this exponent has a little something to do first, the x minus 4. The minus 3 is big. See the difference? That's an exponent, and that's outside the exponent. All right, guys, good job on us getting one done. You have a couple more practice problems if you want to keep final reviewing on your own. And if you get stuck on something, or if you want to come ask me questions about domain, range, exponential graphs, or maybe how we simplified, come find me during lunch, after school, period 7. But for right now, we have a homework due. All right. Colored pens. Out. Homework spiral open. Is this the one from last night? I'm answering the question as soon as we make sure we're pointing people in the right direction. Go find me 37, the one we're trying to get on time. I'm so sorry. I heard a voice, but I don't know who it was.
I heard that.
As soon as you finish grading, there's one assignment. We'll pop into section 800. Remember, some of you felt really weighted down. We were just trying to get this one in and on time yet, right? All late work, all makeup work due by next Friday. If you need any help, especially with test corrections, because they're worth a lot of points, come find me. Okay, we're going to go grade. Here we go. So this is the one that hopefully you guys were finding, page 429, 7 to 10, 23 to 25. For those of you that don't have this homework ready, write down the next homework. It's a much easier as far as it's just 3 through 11 and 19 on page 436. You get it written down in your homework spiral. So here we go. Number 8, you were trying to graph. Did you guys figure out that it was a concave down graph that had been shifted down 7? They used a really snazzy, instead of using the vertical flip terminology, or the flipping down, it said reflection in an x-axis. If you look in a mirror, there's a reflection that's jumping back in. This parabola was reflected across the x. And then they said vertical translation. We can also use the word shift. Shift down 7 is the words, or are the words, I should say, for describing what happened. Number 10 was also one of those reflections in the x-axis. That up. Now, hold on. I realized when I was working with one of your classmates yesterday, when the book says something like compare to x squared, some of you might be getting a little bit confused because you're not realizing x squared was that very first guy we covered before Thanksgiving break that has points like 1, 1, and 2, 4, and negative 1, 1, and negative 2, 4, and 0, 0. This is what they're having us compare to. They're having us compare to the super basic guy that has no numbers multiplied in front and nothing added or subtracted at the end. So that's why it's a flip, because it's going the opposite direction. Okay, snazzy word for flip, reflection. And that's why there's a shift down, snazzy word translation, because we're comparing to that guy. So this one, not a shift down, but instead a shift up. Now here's the cool thing. If you did your tables correctly, and if you did your sketches correctly, you could have looked at them and compared and maybe used words to describe just fine. But if you understand there's a pattern, maybe you can use these wordings or these changes to actually double check your work and make sure you did it right. For instance, if it says a translation 7 units down, okay, I see it, but look at the equation. There's a minus 7. And if this one says, well, wait a minute, it has a plus 1. Maybe before even graphing and doing a table, you can kind of get the idea there's a translation up 1. So if your graph doesn't shift up 1, well, you did something wrong. And I was actually able to check someone's answer yesterday and be like, oh, hey, check it. Your equation has a plus and your graph went down. Something's wrong. And that's something that they could have checked on a test or could catch themselves on a test and be like, oh, hey, if I know this plus or minus thing shifts up or shifts down, man, maybe I can use it as a way to make sure my answers are right. And then we have that negative in front, which both of these have. Maybe another way to double check that we're right, those negatives in front should always have that concave down shape. And the one change in this one is that he also had a 3. So that 3 had that pulling the rubber band, the vertical stretch by a factor of 3. Anyway, just wanted to show you guys a couple things as to the equations and how these transformations, we call them, these changes, actually come straight out of the equations. And I had a calculus kid who was listening in on yesterday, one of your classmates and I talking about your homework. And they started laughing because they were like, oh man, this is just the beginning of you guys looking at equations and having ideas about what's going on in the graph before you actually graph it. So my computer's frozen. That's fun. I'm really trying to play it off. Oh, it doesn't scroll down anymore, sorry. Because it's way down here. Can I zoom in? The bottom answers are really tiny and they're kind of hidden. You guys see them? X equals 3 and x equals negative 3 are the zeros for 24. And 7/9 is the 0 for 44. Guys, I have your book open right over here. Is there something that you guys want to ask on the last night's homework section 8.2? Either directions that didn't make sense or odds or evens where the answer didn't make sense. Or, I guess the answer makes sense, but I don't think I could have gotten there by myself. Anything? You sure? Yeah, Jonathan.
So when you make a table for
the graphs?
Yeah. You just use for the eggs, you use -1, 0, 1, 2.
Yeah, that would be okay. I think in class, I'm usually doing 5 points, -2, -1, 0, 1, 2. But to be honest, if you notice with the ones we did today, 3 points were enough for our exponentials. You just want to make sure that you have enough to see before the min and after the min to see the full shape, or before the max and after the max. Because as soon as you get, well, in with Miss Sutherland, or even in geometry, how many points do you need to make a straight line? 2. I need a starting point, and I need to know what direction to go. I need another point, and then boom, line. How many points do you need for a graph? At least 3, 4 would be better. Because if you have like 1, 2, 3, does it keep going? Does it level off? I want to have 1 before the vertex and 1 after the vertex. So technically you want the vertex and 2 more. Because if you have the vertex and 2 more, you have enough to make your swoop. So Jonathan, technically if you have your vertex and 1 on one side, 1 on the other, 3 is enough. 4 or 5 is just being safe. Is that good?
Yeah.
Okay. Anything else from homework? Sorry. Yeah, Andrew.
Number 10.
Number 10. Number 10 is this one that says to graph. I think probably if the graph got sticky, it was because the plugging in got a little weird. So let's make sure our PEMDAS is going okay. Jonathan, can you use your trick and just maybe do a few points? My computer comes back. Hold on. You know what? I think I have a white marker selected. Never mind. It was my fault. Okay. X and then Y. This is -3 times something squared plus 1. PEMDAS. Once I put something, go behind the board, please. Thank you. PEMDAS. Once we put something in the parentheses, we have a squaring, a multiplying, and an adding, and there's a clear PEMDAS order to that. So, squaring, a multiplying, and adding, a clear PEMDAS order. Let's go ahead and do that. -1, 0, 1, and see if it's enough. Because I know you guys are trying to do it short and sweet. So if you were to put in a -1, PEMDAS says to square first, right? So then -3 times 1. PEMDAS says to do what next? Multiply to -3 plus 1. And then -3 plus 1? -2. Good. So then in my graph, well, maybe I should see what the other values are. So I'm not exactly sure what to make my y. So I do know my x's are going to be -1, 0, 1. Okay, plugging in 0. I'm just going to go ahead if you guys don't mind. That didn't work at all. Let's just erase and start over. Follow the exact same PEMDAS. Square it first. Multiply next. And then add. And plugging in 1. Andrew, see I'm being very particular with my PEMDAS?
Yeah.
Good. Plugging in that 1. 1 squared is just 1. Times -3 plus 2. Multiplication next. Addition last. So now I see I don't need very many y's. I'm just going to go by 1s to make enough room for myself. I have my 1, my 2, my -1, my -2. If -1 is -2, and if 0 is 1, and if 1 is -1. I think I have enough. Oh, do you guys? Some of you are noticing that it's supposed to bounce back and forth and like copy each other. My 1 randomly became a 2. Did anybody were you staring at that? I'm really confused. I'm really confused. Yeah, that was supposed to be a +1. My bad. A -3 plus 1 would be -2. There's that symmetry. Got it. Otherwise, my parabola was kind of funny and kind of sideways. Sorry, Andrew.
Okay.
Now we're good. Were you guys doing domains and ranges last night or something? Or were you just graphing and describing? Perfect. Thanks, guys. Keep this homework out. Don't put it away. Come on, come around and make sure you get points for working on it. And I see lots of tables. Actually, you know what? Real fast, can you just hold up for me? Let's do a hold up one today. I'm going to be looking for tables and graphs. There should have been some words. I'm not going to make a big deal about it. And once I make eye contact with you, if you have a second page, just go ahead and flip and let me see that second page, okay? All right, first row, let me see it. And you have your graphs and graphs. Good. Good. Okay. And we can talk today maybe about that. Maybe tables now that you know about 3 points, okay? See a problem, yeah? Finish it and then show it to you later. Third row, sorry. Andrew, I'm sorry. Graphs are really good. Try to make the graphs a little bit bigger and get some words in there. Tables and graphs. Okay, be sure that you guys are thinking about the words. Right? You see how it was up there, stretching and the reflection.
You can't put all these targets in the box.
I know, but you know.
I can have an extra one, I can remove it. With the ones, what is it?
I'm like, no, hours. Because I got iron board here. So it's basically iron your clothes, and then you put the line, you put the board in your mirror. And iron.
No, I actually don't like mine though, because mine's like, ours like it's like a stoplight, right? Or like it tells you like how much time you have left.
No, but
Like
That's better than I got.
Like how much time you have left on the red light.
red,
you
and
know
then
those
for
like
green.
things where they like you like flip them over and then
You know,
Yeah.
hours. Yeah, it's hours. It's basically that.
it's that, but a stoplight sign. So it's like that, and then it shows you how much more time so you can go. Now I know it. I know it's like.
What'd you get?
All right, need to go talk to one of your classmates about their homework last night, but that's totally fine because you guys, thank you so much. It was a much better participation than last time. All right, guys. Here's the struggle. Here's the struggle of this section. You ready? Adrian. Notes open. You guys can put away your homework except for if you need to show me something else about the homework. But if I've already checked it and I've moved past, go ahead and put that away. Notes open. You guys have been noticing every single section we're adding something onto x squared. So our big parent function is y equals x squared. What changed in section 8.1 is we said, hey, that's not it. There can be an a positive or a negative number that makes it go up or makes it go down, makes it be stretched or makes it be shrunk, so that means narrower or wider. In section 8.2, it said you can also have an addition of just a number, a positive number or a negative number. At the beginning of class yesterday, we totally did a summary page of what's going on with the A, that's section 8.1, of what's going on with the C, that's section 8.2. That is a rough marker. No wonder it's not. But guys, check out 8.3. What's new and what's different this time? It's going to make a bit more of a mess. What's new and what's different this time? Look at that title at the very top. Do you see it? There's a B, and the B has also an S. Section 8.3 says we're adding in a whole new term. And we now have to figure out what's going on with him. Now the crazy thing is, you guys dealt with stuff that looked like this, like non-stop. chapter. Because we were factoring these guys. 2x squared minus 3x plus 1, x squared plus 5x minus 6. You were factoring them, but you weren't graphing them. You were thinking about the math of how to find zeros of them. But we were never looking at the picture of the parabolas or the quadratics. It might be a little bit discouraging because some of you guys might have just heard me say this bx comes in the middle and kind of messes everything up. But there are hints, there are formulas, there are tricks to not let him totally mess it up. Or isn't going to be quite as easy as the others. But it makes sense why it was hard. Alright, thanks guys for getting your notes set up and ready to go. So let's go ahead and fill in some information that we have, okay? Concavity. The nice thing is, even though there's that, check it, the only new thing is this middle dude. Even though this middle Bx is new, we still have A and we still have C that's going to behave the way you guys have been thinking. Which means, for concavity, up versus down. Can anybody help summarize for me? When looking at a quadratic with numbers plugged in, which one tells me whether it's going to be facing up or whether it's going to be facing down? No. Not these ones. I'm guessing that you're saying these ones, Levi. These are the two addings. That's actually looking at B and C. So you set your power deduction to say it's not those guys. What's the only other guy left? A, yeah. Okay, so it comes from A. Question. If you're a generally positive person, a generally positive, there's a snazzy term for that, optimistic, right? If you're a generally positive person, optimistic, are you going to be frowning a lot? And you might have like a somewhat natural frown. That happens sometimes. There's like an old actress who like always looked like she was frowning even when she was happy. But generally, if you're an optimistic, positive person, you won't be frowning all the time, right? Why am I saying that? If you're a positive person, if A is positive, which one does he go with?
The happy one.
The happy one. Easy.
Because you're positive.
Yeah, exactly. And if you're a negative person, well, sometimes negative people are the ones that are like laughing the most, but not in like nice ways, right? But we can say, if you're a negative person in general, we'll say, okay, you'll be frowning more. Okay? So positive versus negative. And you have to think of who, though, because as Levi said, there are pluses and minuses and all this. You have to look at the leading coefficient. And that's something we learned with polynomials, the leading coefficient. The leading guy, the lawyer whose name is on the building, right? The main guy. Is he positive or is he negative? He's going to set the tone for the whole thing. Okay? So, positive up, negative down. Y-intercept. He's the easy. Because to find the y-intercept of, and remember, bx messes everything up. Makes everything harder. We need some extra clues to help us graph it, because Jonathan asked me today, are 3 points enough? And I said yes, as long as one of them is the vertex. The sad thing is, guys, as soon as you have a B, you haven't just gone up, down. You haven't just stretched or flipped. You've actually now moved the parabola somewhere else. So negative 1, 0, 1 might not help at all. Negative 2, negative 1, 0, 1, 2 might not help at all if it's not centered anymore, but it's somewhere else. So to help us with that, we have to look for some more clues. But the nice thing is with lines, you guys totally had to do y-intercepts. Y equals mx plus b. But in parabolas, it's not quite as easy as just stealing a letter. Instead, we have to plug in x equals 0. And then solve for y. It's going to give us a hint as to where are you, parabola, because it's gotten moved somewhere. So actually factoring is going to come back in and be really helpful also. But not yet. That's going to be a future section. If you can factor a quadratic, he gives us more clues and more hints when we start putting everything together. But for right now, you know if he's up or down from the positive or negative leading coefficient. You can find that y-intercept if you just plug in 0, which is one of the easiest numbers to plug in. The axis of symmetry and the vertex just got a little bit harder. Because instead of section 8.1, where the vertex was always 0, 0 if none of that was there, or instead of section 8.2, where we can take 0, 0 and just go up or down to find the vertex, and it was still nice and centered right here by the axes, maybe up, maybe down, but it was still right there on the y-intercept. Now that he's gotten shifted away, we have to use a formula. And our formula is going to be negative b all over 2a. Now I know just a few of you guys have learned what's called the quadratic formula before. And there's a song that goes with it. This is not that. It's shorter, and it's not for the same purpose as the x equals negative b plus or minus squared, b squared minus 4 is equal over 2a. Some of you have no idea what that is, and that's fine. You don't need to. But if you have ever heard that before, we're not quite there yet. Shorter formula, easier formula, to help us find the axis of symmetry, what to fill in this box, which is the same thing as the x of the vertex. But then, Jonathan, we're back to what you asked me. If I can plug into the little baby formula using the b from right here and the a from right here, if I can find my vertex, all I need is 1 point on this side, 1 point on that side. I don't care where you are, I can find you. This little formula is going to be super important. If you're a highlighting, starring, colored pen kind of person, I would put a star, I would put a highlight, because negative b over 2a is going to make things a lot easier. So we're going to solve for x using the formula. And once we solve for x, because the vertex is a point, we can solve for y. Or another way of saying it is we can set up a table. But instead of, and some of you guys aren't even doing the table, it's super dangerous because you're pretending like you know exactly where to put the parabola. And some of you are doing it on scratch paper. And I'm seeing the points, so I know you're finding them. But it's going to get messier because we just shifted this guy away as soon as that bx came in. So how do we do a table? Not negative 2, negative 1, 0, 1, 2. It's not going to work anymore. We're going to take this vertex. We're going to put him smack dab in the middle. Our vertex is going to get that middle spot. And then all we need is 1 to the left, 1 to the right. Swoop, there he is, and we'll find him. Remember, it's a quadratic swoop. It's that full curvature, not that exponential one. Let me freeze the screen for just 1 second. I see a couple of you guys still writing. And I want to see exactly what example I want us to show. We're actually going to do 2 examples. Yeah, I think 2 examples. One of them has a graph, so things are way easier because you can see the picture. And another one just has an equation, so we have to use that formula. The graphs are easy. You get to see it and be like, oh, hey, look, I found them. The equation's like, I don't know where he is. He got moved somewhere. So here's the graph. If you're looking at the graph, this guy has a vertex. He's a parabola. He has to. They all do. Is it the high point or the low point? The max or the min? Or can you guys see the vertex? You can, right? What's that point? Yeah, louder, but I heard it. The x value is... Oh, I heard it. You got it right. So yeah, the x value is 1, and the y value is... Got it. Thank you. It's a graph. I can see them. The vertex is that special low point on a concave up. They don't even give me an equation. Whatever. And if the vertex is 1, 2, the axis of symmetry, back from section 8.1, says I just need the x because the x is that fold line, the line that I would go to x and fold, and I would have that symmetry. I just get to steal the 1. They're the same thing. The axis of symmetry is the vertical line at the place, or at the x, where the vertex is located. But what makes everything a lot harder once the pictures come? Where's my vertex? Ah, he's positive. Yay, I know he looks like that, but where is he? Is he here? Is he here? Is he there? I don't know where he is. I just know wherever he is, he's a positive dude. So pause and wait. What did I have you highlight? What did I have you star? What formula is going to be the key to us figuring out his location? Got it. Say it louder, Max. X equals negative b. So who in this one is my A? Leading dude. 2. Who's my B? The middle new guy, right? Okay. So x equals negative b, 8, all over 2 times 2. Pause. Everybody okay with where all the numbers came from? Negative who? Him. Okay. 2 times who? Him. All right, fine. So what do we get? PEMDAS tells me to do what first?
Parentheses.
Yeah. What's 2 times 2? And what's negative 8 over 4?
Negative 2.
So guess what? We just found our axis of symmetry. What's the other part we're supposed to find? The vertex is an x. Remember yesterday? An x and a y. How do you get a y?
Solve.
Think about like a table, but you don't have to do the whole table. All you got to do is go plug in negative 2 and find your y. I'm going to do it to finish off the video, but you guys can go ahead and go. Homework, right there on the board. Take a picture on your way out the door. I have it written down yet. Yeah. Bye. We got to get stuck plugging in tonight. You can come back and find the video.
Your voice got a little I didn't take much yesterday. You have an X, all you have to do is go find our Y, so it's like the table where we take it
I've seen people. Amy's mom. I'm so bad.
We have to do a lot of undocks, but we've done. Then we do all of our multiplications, which would be 8 minus. And then we would do all of our additions and subtractions.
Good luck.